everyone, and thanks a lot for tuning back on Twitch to join me on this live coding session as part of Innovate 2019 online conference. My name is Will Better. I'm a Senior Technical Account Manager here at AWS, and I'm specialized in machine learning and AI. Today, I'm going to walk you through an end-to-end machine learning example, not only to show you how to build and train a machine learning model, but also to show you how to go through the machine learning process step by step. We're going to start by discovering the data, identifying the business problem. I'm going to give you some tips and tricks on how to identify problems in your data set that you need to fix before you go ahead and train your model. And then finally, you're going to end up with deploying the model and making predictions. So before I get started, I want to give you a little bit of background on what we're going to try to achieve here on this session. I'm going to try to show you a real life example as much as I can so that you can know what exactly happens when someone approaches a machine learning problem. So we're going to try to identify credit card fraud transactions. And we're doing that because it's really crucial and important for financial institution or any business that work in finance to identify any kind of fraud that they might encounter. Not just credit cards, but any kind of transaction that might be fraud. And that applies to any kind of transactions. We're going to use Amazon SageMaker as part of, as a tool that's going to achieve this. For those of you who don't know what Amazon SageMaker is, Amazon SageMaker is a fully managed machine learning service that makes it really easy for developers and data scientists to build the machine learning models, an end-to-end service. You can also use it to have a distributed training across multiple instances that runs on a serverless fashion on Docker. And you can also, Amazon SageMaker also has a bunch of built-in algorithms that you can use out of the box. So you can just grab the algorithm, start training right away without even having to dive deep into the math behind it. Just a reminder, this session is a 400 session, so I'm assuming that you already know a little bit about machine learning, and you know a little bit also about some of the AWS services like SageMaker, like S3, like Lambda, like API Gateway, and so on. Now, we need to go through that machine learning process. You might have seen that slide before. In that slide, it defines and shows you what do we do in order to tackle any machine learning problem. So we start by identifying the problem and framing the machine learning problem into a certain questions. And the answer to the question will determine what kind of algorithm we're going to use to solve that kind of problem. So for example, this specific problem that we're going to go through, we need to answer a question that says, for example, is this transaction fraud or not fraud? So the answer to that question is either fraud or not fraud, or 0 or 1, or yes or no. And that for me sounds like a binary classification problem. So now that we've identified what kind of machine learning problem that we're facing, we need to choose what kind of algorithm that we need to pick in order to solve that machine learning problem. So I have here the documentation for SageMaker, and this is a list of the built-in algorithms we have here. And you can get a little bit more details on what problem each algorithm is trying to solve. For that specific problem, the binary classification problem, we have two different algorithms. We have linear learner, and we have another algorithm called XGBoost, or extreme gradient boost. In this specific example or session, I'm going to use XGBoost to try to solve that problem. And I'm going to tell you why we chose this. But before we go into the why, I want to tell you a little bit more about what is XGBoost. So XGBoost is a supervised machine learning algorithm that belongs to a big family of algorithms called decision trees. So decision trees are basically learning from the data, and it builds a tree like the tree that you see here. So for example, let's say you have an input of age, gender, occupation, and you pass it through the algorithm. The algorithm tries to build that specific tree that you can see here, and it looks at each and every input. So for example, it looks at the age, and it says, for example, if the age is below 15, then let's look at the next feature, which is the gender, right? And the problem that we're trying to solve here is that this person like computer games or not. And then at the end of the tree, we have something called leaf. In this leaf here, we assign a score. And based on that score, we decide what will be the answer to that question. So for example, because it's the first answer is no, we assign a low score, -1. Because it's a yes, then another yes, we assign a little bit bigger score. Because it's a yes and no here, we assign a little bit small score, but it's a little bit bigger than the no. So extreme gradient boost is one of the boosting decision trees algorithms. It's what we call ensemble decision trees, which means it's not just one tree, it's a combination of multiple trees or many different trees. And we get the score out of each tree of the algorithm, and then we combine all these scores together so that we can come up with an accurate model. And that's why XGBoost can be really, really accurate and more accurate than just simply using decision trees. So why XGBoost? Like I said, it's very accurate, much more accurate than decision trees. And the other reason is it can be a little bit more interpretable. So you can interpret the results and the model much better than any other algorithms, like, for example, deep neural networks. And you can actually look at the model and plot and visualize the output of the model in a graph that looks exactly like this. And I'm going to show you this in a later step. By the way, feel free to send me any questions on the chat. I'm going to look at the, I have the chat right in front of me. I'm going to look at the chat from time to time, and I'm going to try to answer all of your questions. So let's get to the code. So I'm using a Jupyter notebook, or what we call a Jupyter notebook, which comes as part of Amazon SageMaker. You can spin up an instance, and that's a managed instance. So everything is installed for you, and you can just spin it up, use it right away. And here, and I'm using it because it's very, very good and easy to use. It's a web-based IDE. It is the industry standard for data scientists to look at the data, process it, and develop machine learning code on it. So here in the first block, you can see that I'm importing some libraries, something like Bluetooth, which is the SDK for AWS services, which gonna help me talk to other AWS services like S3, for example. I'm also importing SageMaker library because we're gonna use it to start the training and doing the deployment. And I'm importing a library called Seaborn, which is a library that I'm gonna use for visualization. And here I'm initiating a role out of the SageMaker. A role is something like permissions. So it's a permission that SageMaker uses in order to access other AWS services. So if, for example, we want to pull out some files out of S3, we need permission to access these files. The permissions are embedded here in that role. And I'm specifying the prefix for the bucket and the bucket that I'm going to use for the training. Again, I'm importing a little bit more libraries here. Something to know are the libraries that are really important and everyone have to use if you're going to do machine learning: Pandas and NumPy. These are two really famous libraries that you can use to put your data in a certain structure, like a table, and do a lot of mathematical operations on them. And I'm going to show you how it works. A little bit more about the data set that I'm using. I'm using a data set, a public data set that I got from Kaggle. If you want to get the data set, you can download it from here. So this data set is a 1 day of credit card transactions from one of the European card holders. It has almost 284,000 transactions, and some of those transactions are fraud and some are non-fraud transactions. So first thing that we need to do is just loading the data set. So I've already downloaded the data set from the source, and I need to load it. So the way to load the data set is just using that function called read CSV and pass along the file. Then I'm just listing some entries out of that data frame, or that structure that we call data frame that looks like a table, so that I can just see the data set and have a look at it just to make sure that I loaded this correctly. And if you remember the first slide, this is exactly the step that we're going to do now. We call it exploratory data analysis, which is basically a data discovery step. We need to look at the data, try to get as much insights out of the data as possible, and try to find some problems if the data set has any problems. So the first thing that we're going to do is just using that describe function. And that function does really nice stuff, like it gives us the mean value for each column or each feature. It gives us the minimum value, the maximum value, some quartiles like 25% and 50%, and the count. And one of the things that I notice here is if you look at the time column, you can see that the minimum value is 0. And the maximum value is huge. It's like 6-figure number. But when you look at the other features, it's a very small number. And because machine learning looks at the data in a two-dimensional space or multi-dimensional space and tries to measure the distance between data points, that means we have a scaling problem. That we have like one column has like really high values, and the other columns are having very low values. That problem exists in the amount column here, and it also exists on the time column. All right, so now we see that we have one problem, which is a scaling problem, right? Now let's go to the second insight that we can try to get out of the data. The second insight is just looking at the target class, which is what we're trying to predict. So we're trying to predict this, if this transaction is good or bad, or fraud or not fraud. And that exists in the last column here. So if we try to see the balance between the fraud and non-fraud transactions, you can see that there's 99% of the data set is non-fraud transactions. And only 0.17% of that data set are fraud transactions. And just to give you a sense of visualization, to imagine it, that's exactly how it looks like in a 2D plot. You can see that there's a huge amount of non-fraud and really small amount of fraud transactions. And that's going to cause a lot of problems if you train the data set as is. One of the problems will be introducing bias in your data. So the training is not going to be accurate, and it's going to have a huge amount of bias. And I'm going to show you later on down the track how to solve this kind of imbalance in the data set. The other thing that we need to look at is whether or not we have any missing values. And luckily, we don't have any missing values here. Another thing that we need to look at is the correlation between the features. And not just between the features and the target class. So we need to know how much the features are correlated to the target class, because that helps in some situations in making the model diverge and learning something out of the data. So another tip that I want to give you here is if you're going to do the feature correlation in the dataset, try to do it after you fix the imbalance problem, not before. And I'll show you why. So I'm doing feature correlation here using what we call a Pearson correlation matrix. And I'm using the printing this using the sns.heatmap library. And that's how it looks like. So the darker the cell, the higher correlation, we call it a high positive correlation. If the cell is very, very light, we call it a high negative correlation. So positive correlation means if the feature goes up in value, the class also goes up. Negative correlation means if the feature goes up, the class goes down, right? But there is some kind of relationship between both of them. You can see that most of the correlation matrix here is plain, like almost no correlation at all. It's sitting at 0. And that's because there's a huge imbalance in the data set. So we're going to try to do the matrix or the correlation matrix again after we fix the imbalance problem. All right, so we've discovered some problems. It's time to fix those problems before we start any training. So the first problem that we need to fix is the scaling issue. To fix the scaling issue, I'm using a library from scikit-learn framework. It's called Robust Scaler, right? Scikit-learn has many different libraries that can be used to scale or fix the scaling problems, but I'm using this specific library because it's robust towards any outliers. So if the dataset is having outliers, Robust Scaler knows how to deal with them. And here I'm just giving new names, which is amount after scaling and time after scaling. And remember, these are the columns that we're having the scaling problems. And then I'm using the library Robust Scaler, and then I'm using the function called fit transform, and that's going to automatically try to scale down the features to match the other features in the same dataset. Again, I'm doing describe to see the results. And as you can see here, the amount after scaling, the minimum value is now much smaller, 3.4, and the maximum value is no longer 6 figures, it's only like 358. And the same for the time here, the minimum is 0.5 and the maximum now is 1.03. Now, the second problem that we need to fix is the imbalance that exists in the target class. And to fix this problem, we have two different techniques, or actually many different techniques to fix that problem. But in this specific case, I'm going to use two different techniques. One is called undersampling, which is basically means I'm going to go to the majority class and I'm going to downsample it. I'm going to just choose a really small number that match the minority class so that I can make them both of them equal. Or the other technique is called oversampling, which is basically doing data augmentation or generating multiple data points that looks exactly like the minority class in order to make it the same amount as the majority class. So what I'm doing here, I'm going to show you the code for both undersampling and oversampling, but I'm actually going to use the data that comes out of undersampling just for the sake of this demo. So for undersampling, as you can see, I'm using the data frame sample function, which is basically taking a sample of the function and shuffle the data set before we use it. And then I'm taking only 492 values out of the data set that matches this specific class, right? And then when I print it out, you can see that there is a matching number of the classes. So the class is now matching and balanced. The other technique here is oversampling. And for this, I'm using IMB learn library. and it has an oversampling function that you can use out of the box. And one of the techniques is called SMOTE, right? And that basically oversamples the minority class. So you just import it and you pass the fit function, and it tries to learn how to generate data samples that looks exactly like the minority class. And after we finish here, and I'm printing the data again, you can see that it managed to generate some data that has exactly the same amount as the majority class. So now both of them are around 258,000 or something. Now you remember when I told you don't do the correlation matrix before fixing the balance problem? Now I'm gonna show you why. So if you look at the correlation matrix from before, you can see it's very plain. It's not really giving us a lot of information, and that's because there's a huge imbalance in this specific data set. So after fixing the imbalance problem, you can see that, yeah, now we're getting a little bit more information. Now you can see the really high positive correlation, the really high negative correlated features with the class target or the class feature. So I'm going to pick some of these features that are really strongly correlated with the class, either positively or negatively, and we're going to do a little bit further analysis on these features. We need to identify if those features are having any outliers or any anomalies, because if they have outliers and they are strongly correlated with the target class, that's going to impact the overall model accuracy, and it's going to introduce a lot of problems in our model. So here I've identified 3 features, V17 and V14 and V12, that are negatively correlated, and 3 other features that are positively correlated. And I'm going to use a technique called box plot, which is simply a visualization that shows you if there's any outliers in this specific features. So the box plot looks exactly like this. It has a rectangle. In the middle, there's a median line, which is the median cutoff of the data. We have an upper quartile here as boundaries and lower quartile. And we have upper whisker and lower whisker, which is these 2 lines here. Anything beyond these boundaries, anything out here or out there, we consider them outliers, and they are not desirable. They're not good data points, so we need to get rid of them. So one way to do this, I'm using SNS, which is part of the Seaborn library, and I'm calling the box plot function. And I'm giving it the 3 features that we identified in the earlier step, along with the normalized data frame that we've done that has the balance of the target. Now we can see that these features are having a little bit of outliers as well. So you can see there's one outlier here, another outlier here, and another outlier here. So we need to get rid of those outliers before we start training the data set. So in order to do this, let me try to make it a little bit bigger so you guys can see it better. So in order to get rid of these outliers, I'm running a query on the data frame. So the query is very simple. I'm saying that features V17 take everything that is above this number, which is -7, in this specific class, which is the num-fraud. So after running this query and concatenating everything that comes out of that query, you can see I'm going to try to print it again. And as you can see, we got rid of the outliers. So we no longer have any outliers in this specific class, which is 0. Now I'm going to do another shuffle on the data set before we go ahead, because we just need to make sure that there's no certain sequence that was built up during that cleaning process. And then after that, we're going to split the data into training dataset, validation dataset, and test dataset. We're going to use the training dataset for training, the validation dataset for the evaluation during the training process, and the test dataset is going to be a complete new data points that the model hasn't seen before during the training, so that we can see how it actually works in real life and whether or not it's going to identify the fraud and non-fraud transactions. And I'm saving the training dataset. I'm using a really simple numpy.split function, and I'm giving it the data frame, and I'm specifying that 70% of the data is going to be the training, and the other part is going to be for, or 20% is going to be for validation, and 10% of the data is going to be for testing. After we save it to a file, I'm uploading this file to S3 bucket because SageMaker receives the training data or the training data set from S3. Now here, this is where I'm actually starting the training. So I'm importing some libraries here, a library called getImageURI, and that's just to get the image or the Docker image that has the built-in algorithm for XGBoost. After I get that container, I assign it to that variable, and I pass it on to a construct called estimator. So the estimator is just a big construct or big object that contains all the information that we need for the training. So something like the container, the IAM role, which is the permission that the training needs to pull the files out of S3, the training instance count, which is simply how many instances we're going to train on. And like I said, it's very scalable and it supports distributed training. So if you want to train on 10 instances and you want to get really fast kind of training, you can just simply put 10 here. Let me delete that. I'm only going to train on one instance because it's a small data set. And this is the instance type that we're going to train on. And of course, you need to pass also the session because it contains some information that the training needs. Now we're going to set what we call hyperparameters. The hyperparameters are simply the configuration or the parameters that the model needs in order to build that algorithm. Something like how many layers in that decision tree or that boosting tree. What is the maximum depth? And how many times should I go through the data set in order to learn, which is the number of rounds? What is the objective metric, the objective that we're trying to achieve? Is it regression or logistic regression or binary classification or multi-class classification and so on? After we define the hyperparameters, we call the fit function. So the fit function starts the training process, and we're passing here the training input and the validation dataset. I'm going to read some of the questions now.
Explain training instance.
So the training instance is the instance type that we're going to train on. So within AWS, we have what we call EC2 instances, which is basically like a machine that has CPU and memory. And we have different types for these instances, something like M4 X large, M4 2X large, and so on. So each machine has a different configuration, like a different CPU to memory ratio. So M4 X large, for example, maybe, I can't remember on top of my head, but it might have like 2 CPUs and 4 GB memory. If you go M4 2X large, that's 4 CPUs or 6 CPUs and 16 GB memory and so on. So the more you go in size, the more configuration that you're going to get out of that instance type. So I hope that answers your question. Any other questions? Let's see.
Okay.
So here I already started the training process using the fit function. And this is a log output out of that training process. It is just giving us some information around the trace that has been built and the error or the objective metric that we're trying to achieve. So what exactly is the error? You can see here at the end of the training, the last validation error is 0.06. 0.06 means 94% accuracy, which means if we have 100 transactions, we're gonna make 94 transactions. We're gonna make right predictions for 94 out of the 100 transactions, and 4 are gonna be misclassified. 4 are not gonna be accurate or wrong kind of predictions. So that's a really, really good number. But at the same time, I'm not gonna stop here. I'm gonna try to tune that model, and I'm gonna try to get a little bit better results. But let's go through the model deployment first, and let me show you how can you evaluate your model after you build it. So after we train the model, we need to deploy the model. Deployment means we're putting the model artifacts, the model that we trained and generated, inside an EC2 instance. And we're making this instance available for you or for anyone that you send an API command and get results and predictions. So when I run this, in the background, it's gonna start an EC2 instance. It's gonna pull all the model artifacts that we trained from S3. It's gonna put it inside the instance. It's gonna build an API inside the instance, and it's gonna publish that API so that you can send requests and start making predictions. So now that we built it, we're gonna send the training data set here as a whole, like that 10% of the data that the model haven't seen before. We're gonna start making predictions. So one way to evaluate whether or not our model is good or bad, we use something called confusion matrix. So the confusion matrix, it just looks exactly like this. On the top right hand corner here, you can see a false negative. And in the bottom left corner, you can see the false positive. So the false negative and the false positive is how many times the model made a mistake, like didn't predict the actual value right. And the true positive and true negative on the top left hand corner and bottom right hand corner, that means how many times the model actually predicted the right value. So when I passed the whole test data set, I got this confusion matrix, which means I made 48 right, true positive, and I made 46 true negative, but I made 5 mistakes here, right? Which translate back to the 96% or 94% accuracy that we discussed before. Now that the model is created and is giving us like fairly good results, but not as good as we would like it to be. So we're gonna start the model tuning. And there are many, many different ways to tune your model. One of them is to look at the data set and try to do a little bit more feature engineering, enrich your data set, or which is what we're gonna try to do here, is tuning the hyperparameters, which are the hyperparameters that you've seen before the training step. Again, there are too many different ways to tune the hyperparameters. One of them is manually, like trial and error, because it's not intuitive. So you need to go change the hyperparameter, start the training, see if you're gonna get better results or not. Another way to do this, which is much smarter way to do it, is to use machine learning on top of that machine learning in order to identify the right hyperparameters. We call this automatic model tuning, or in different words, we call it hyperparameter optimization. It uses a machine learning algorithm called Bayesian optimization. and it tries to find the areas of, explore the areas of space to find the optimal region. So just to give you an idea how it looks like, that's an actual experiment that they were using the Bayesian optimization algorithm to try to make it hover over that specific point that you see here. And as you can see, the model tries to find the whole region that has the optimum hyperparameters. And once it finds that region, it tries to explore more and tries to get the best hyperparameters out of that region. And as you can see here, that's the end result of the model. You can see that the drone is being optimized, and now it is hovering very accurately over that point. Now we're going to try to use exactly the same technique on Amazon SageMaker. Luckily, Amazon SageMaker has given us that algorithm out of the box. It's already built. All you need to do is just specifying the space that you need the algorithm to look at and search. And the algorithm is going to do all the magic behind the scenes. One way to do this is just to do it from by running the hyperparameter tuner API call and give it the parameters that it needs and specifying the range. For example, ETA, you want it to look for values between 0 and 1. Something like the maximum depth, you want it to look for values between 1 and 10. Another way to do this is through the console. So let me switch to SageMaker console and go click on the hyperparameter tuning jobs. And this is a job that I already ran before, but in order to show you how it looks like to create a job, let's clone it. And all it needs is just a name. So we can give it a name, something like this. And then ask you for execution role, which is basically some permissions that it needs to access other AWS services. It's going to ask you for what algorithm you're trying to optimize and search for. And it's going to give you the hyperparameters that are supported for this specific algorithm. Now you can see all the hyperparameters that are very specific to that algorithm. As you can see, like some of these hyperparameters are already pre-populated for you. You don't really need to specify all of these hyperparameters. You can just specify the hyperparameter that you need to tune or to make the algorithm search that space for you. So here I'm specifying the number of friends and specifying that hyperparameter called ETA. I'm specifying another hyperparameter called gamma and the maximum depth. If you want to understand and get a little bit more insights what each hyperparameter does, you can go to the AWS documentation, like here. And if you go to the XGBoost algorithm, let's expand it, hyperparameters, you're going to see detailed explanation what exactly each of those hyperparameters do. All right, let's go back to the notebook, the SageMaker console. Now that we've defined the space that we need, we go next. All you need to do is just specifying the input location for the training dataset and the validation dataset. And this is exactly the same training dataset that I use for training the model here in my notebook. And then after that, you're specifying the output location in which you're gonna put the model artifacts after the tuning. So I've already ran it because it takes a lot of time to run before this session. And as you can see here, it took around 2 hours and 8 minutes to finish. And it ran many different training jobs. And each training job, it was looking at the objective metrics, which is the validation error. And the best output or the best training job, we put it here in this tab. As you can see, the best value for the training or the validation error was 0.27, which means like 98% accurate. This is so much better than what we could get with the default hyperparameters. So if we scroll back to here, that was the output that we got with that hyperparameter tuning. And this is the output that we got after the hyperparameter tuning. It's much, much better. And it also shows you the hyperparameter that this specific job used in order to get to this results. So you can see, for example, the maximum depth. The maximum depth here is 9, which is the best maximum depth to get you the best results, and so on. Now let's go back to our notebook. We finished this, we did the tuning. Now in this step, I want to show you how to take that model outside of SageMaker and try to load it into memory and do predictions without having to spin up something like the endpoint or a machine that runs 24/7. So one way to do this, I'm using the XGBoost library itself. I'm using another library called Pickle, which is basically loading machine learning models into memory. And I already downloaded the memory from the model out of S3, and I uploaded this model onto the notebook instance. And then I'm using Pickle to load the model. And then I'm using the predict function in order to make predictions on one transaction, which is here. So this transaction, the model hasn't seen before at all. I actually had that transaction here. Let me show you. If I can get to it. So I already copied that one, and I already know the answer for this one, this transaction, which is non-fraud. Now, if we run this block, we're going to get this result, which is 0.0016, which is very close to 0. And that's exactly how you would make predictions on the fly after you load the model, after you train it. Now, if you remember when I told you why did I choose XGBoost model, I chose it because it's really easy to interpret and because it's very accurate compared to other decision tree algorithms. What I meant by interpret or easily to be interpreted is that I can visualize each and every tree, and I can know based on what did that model make that decision. So if we look at tree, for example, number 3, and I'm using a library called plot tree, you can see something like that, which is a little bit similar to the image that I showed you in the beginning of that session, but a little bit more complex. So you can have, for example, you know that it looks at feature number 13, and if that feature is below -3, then we're going to go to the next feature. And if that next feature is below this number, then we're going to go here, and it assigns a score at the end of each leaf. And then it combines the results from all the trees before it returns any predictions or any probability whether this transaction is fraud or not fraud. So it's not just one tree. We call it a forest of trees. We can try to print out another tree. And as you can see, it's a complete different tree with complete different criteria, something like F9. This is the start of deciding whether or not this transaction is fraud. And then I want to, because we're very limited on time, I don't think we're going to have a lot of time to do the model on API Gateway and Lambda, but I'm going to put all the instructions in the GitHub link so that you can refer back to it. Actually, the GitHub link is at the beginning of this notebook here. Feel free to go pull that notebook and play with it. You can also download the dataset out of the Kaggle link that I provided here. This link, and feel free to play with the dataset. And then finally, I just want to refer you to some useful resources that can help you get started with SageMaker or understanding these concepts that I talked about a little bit better. So for example, for SageMaker, we have this documentation, the AWS documentation. For XGBoost algorithm, if you want to understand how it works internally, you can refer back to the XGBoost open source documentation. If you want to know the difference between oversampling and undersampling, you can refer back to this link. This article here explains why correlation matters and why do we do correlation as part of the data analysis and data exploration. And then here it explains what is correlation matrix and what do we use it for. And finally, this is the hyperparameter optimization link that explains how it works and how to do it using SageMaker. And I think that concludes my session. Thank you so much for sticking out to the end of the session. I'm going to stay a little bit more time and spend more time answering your questions. So feel free to put your questions on the chat, and I'm going to be answering all your questions before I go. So thanks again for joining me. I hope you guys enjoyed the session, and I'll be signing off Twitch now. Thank you.